Well, yeah, I've got a headache just thinking about what we're gonna do now, and it's probably best if you think of this as taking a long walk. Still left, right, left, right, left, right. You can do it. It just takes a long time. And the first thing we have to, well, what we want to do is get to Cramer's rule for a system of three equations and three unknowns. First thing we have to discuss is how to find the determinant of a 3 by 3 matrix. So let's do that. Now again, um, look, there's some aspect of this which is extremely easy, and then there's some aspect of it which is really not at all. So let me talk about the easy part first. So let me go ahead and write down the 3 by 3 matrix. Just any old, I'm picking numbers at random. So let's say 4, 2, 3, negative 5, 3, 1, and 1. Let's say, gee, that doesn't really matter, but how about negative 2, negative 3. So here's a 3 by 3 matrix. Now, to find the determinant of this matrix, all we're going to have to do is regular old addition, subtraction, multiplication, division. And there's a relatively simple rule that tells us how to do it. So I'll tell you what, let me go over that first, the simple part, and then you may be concerned, or you may have some kind of consternation, or you may feel uncomfortable. And if you do, I think that's actually natural or appropriate, or you really should. But let's put that aside. Let's just, how do you find the determinant? Now, again, you can write DET for determinant out in front here. The most common standard way people do it is just write these. They look like gigantic absolute value signs, but that's what it is. Now, let me just show you the how to find the determinant, because the how is easy. A little time consuming, but it's easy. So here's what you do. The first thing you do is focus in on this first entry. And in your mind, block, or I just did it on the board, not really in my mind, block that out. And you're left with a 2 by 2 matrix. Find the determinant of that matrix. So let's go ahead and do that. So that would be 3 times negative 3. Minus, again, I've got to be really careful with the minus signs and plus signs. Minus, because it's this times this, minus this times this. So negative 2 times 1. And we can calculate that, no question about it. Negative 9 plus 2, so negative 7. Find that. I don't want to worry about the calculation right now. We're going to take that and multiply it by this number. This first, well, the element in the first row in the first column. Again, there's lots of terminology revolving around this. I don't think we should worry about that terminology now. I'm not going to test you or quiz you on the terminology, but the method, the procedure here, yes, I do want you to know the procedure. Now, what are we going to do next? Well, whatever we do next, we're going to subtract the value we get, what we do next. And what we're going to do next is, let me see if I can erase this here a little bit like that. Focus on the element in the first element in the second column, and block this out like that. Let me get a fresh marker here. And if you look at what I haven't blocked out, I have not blocked out this number, this number, this number, this number. That's a 2 by 2 matrix. We're going to find the determinant. And not only going to find the determinant, but we're going to multiply it by this term. So first we blocked this out, or masked this out, found the determinant, multiplied it by this number. Then we use this entry here to block out part of the 3 by 3 matrix, which results in a 2 by 2 matrix, and we find the determinant of the 2 by 2 matrix. So let's go ahead and do it. We're going to multiply by this element. So only thing is we're going to subtract here. Now, maybe I should address some of the complex questions. One of them is, why are we doing it this way? Or what does this mean? Just put that off to the side for right now. Let's just say this is just a procedure, and we want to follow this procedure. So we subtract this number times the determinant of the resulting 2 by 2 matrix. So -5 times -3 minus, because we multiply along this diagonal and then subtract the product of the elements along that diagonal. So minus 1 times 1. And then finally, we look at this entry, the first element of the third column, and we block out these two rows. And now we're going to add. So we left this positive, or we left this the value that it was, but in a way I could have put a plus sign there. It'd be a little bit weird to do that, but you could. Put a plus sign there, minus, plus. So there's this alternation that's going on. What do we have left here? We're going to have 3 times -5 times -2. -5 times -2. That's those two numbers right there. Minus, we're going to find the product of these two. So 1 and 3. Now, can you calculate this? The answer is absolutely. It's easy. Piece of cake. What's involved? Just a bunch of regular, in fact, look, whole numbers, just a bunch of multiplications, additions, and subtractions. So let's go ahead and do it. This is the bit, I mean, all this, it seems like a long walk. No step of it is particularly difficult. What you may be wondering is, where are we going with this? Or why would anyone do this? Or why on earth is it the way it is? But just, we're putting those questions aside for right now. Let's go ahead and calculate this. Let's just leave this 4 alone for a minute here. 4. And then what do we have in here? We have, again, I know I said a second ago, but -9 plus 2 is -7. And then, well, that's the first term there. -2. What do we get in here? 15 minus 1, so that's 14. And then plus 3. And what do we have in here? 10 minus 3, 7. And we'll just wrap this up. This is -28. Oops, equals. That's still on screen? Yeah. -28. Let's see, -28. This is just coincidence, those two numbers are the same. Then plus 21. That's -56. -56 plus 21 is what? -35? -35. So the determinant of this 3 by 3 matrix is -35. Now, let me quickly address a couple of questions. Oops. Number one, what is this, though? What does it mean? For right now, let's just say it's a strange, bizarre game. Are there meanings to this? Yes, there are geometrical meanings, there are physical meanings, there are meanings. But for right now, let's just say that we don't want to talk about that right now. This is a procedure. And the procedure says you knock out the first column in the first row, calculate the resulting determinant, and multiply it by this term. Then proceed 2 by 2 matrix, multiply it by this, but you subtract the product. And then finally, we get this final 2 by 2 matrix by masking or knocking out this row in this final column and multiply by this. So that part of the procedure is easy. Is it boring? Yeah, it is. Is it tedious? Yes, it is. Is it time consuming? Yes, it is. Is it fun? No, I don't think it's fun. I mean, ultimately, if this didn't have some uses, I don't think anybody would ever do this. The entertainment value of this is definitely not great enough to cause me to stay up late and do this for entertainment value. Nonetheless, this is the determinant of a 3 by 3 matrix. Now, you can maybe, I don't know if it's obvious or not, but there's an obvious extension to this. You can go to 4 by 4 matrices and 5 by 5 matrices, but we're absolutely not going to do that. Absolutely not going to do that. But if you had a 4 by 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, you would just start with this term and knock that out, and you'd have a 3 by 3 matrix. Now we know how to find the determinant of 3 by 3 matrix. So you find the determinant of 3 by 3 matrix, you multiply by this and continue on, and you alternate with the signs. Again, I haven't even said why. I haven't even said what this all means. But this is one of those moments where I do want to tell you, yes, there are great uses for this. If you continue on down the road of science, engineering, economics, you're bound to see some fantastic uses for some of these things. So you just have to hang in there. It's a little bit like the wax on, wax off, or paint the fence from the old Karate Kid movie, if anyone watches it. I'm not really sure it's worth watching, but hey, for what it's worth. Yeah, I used to say, the old man made the kid wax on, wax off, and paint the fence. If the kid had left, if the kid had said, "Hey, old man, I'm out of here. I don't know. I came to learn karate, and you got me doing these chores." The kid never would have seen what the point of it was. And I realize most people are really in that position when it comes to mathematics. They learn this, and it's some crazy thing, wax the floor, paint the fence, find a 3 by 3, determine it. But if you don't stick around long enough, you never get to see what the point of that was. But I assure you there is a point. Now, let's say we have a system of three equations of three unknowns. So we have 5x plus 3y plus 7z equals 1. Now, I'm not going to actually solve this right now, but I'm going to show you another way we could solve it. Let's say 4x minus 2y plus 3z equals 8, and negative 3x plus 4y minus 2z. I put those slashes on my z's because they tend to morph into 2's. Equals, let's say, 0. We can solve this by substitution. That's very straightforward, very time consuming, not very fun, but great skill builder, and I wanted you to do that, and I'll ask you to do that on the test. I would not only ask you to solve by substitution, but to show your work. Fine. There's the elimination method. Great. There is a Cramer's rule for this, and it's exactly analogous to Cramer's rule for a 2 by 2 equation. How do you solve for x? You find the determinant you get by doing the following. Oh, hey, yeah, I mean, that's not a matrix, right? But remember what we said. If you remove the variables, let me just go ahead and do that. We can remove the plus because we assume if I write 3, it's positive 3. The negative, of course, I need to leave in there. And then, let's see here. All this. Beauty of the whiteboard technology. Oops, we don't need the equal sign. There we go. I said no pluses, right? Yeah, there we go. So we have this associated matrix, the matrix which is determined by the system of 3 equations and 3 unknowns. What this capital D sub x means is yeah, sorry. This is definitely enough to give you a headache when you think about, like, when you contemplate actually doing the calculations. For a 2 by 2 matrix, what did this mean? This meant that we got rid of the column, the x column, and we replaced it with the coefficient column, the final column over here. And we're going to do the same thing here with the x. What we would do is get rid of this. So instead of this, we would use this column. So you bring this column over here. So once we got rid of that, brought that column over there, that would be a 3 by 3 matrix. We can find its determinant the way we just did. That's what this is. Divided by this. And exactly analogous to the 2 by 2 situation, what is this determinant? This determinant is what you get when you just knock these out. And then, of course, if we just proceed in an analogous way, this is this, and z is this. Now, that's fairly poetic, and it has a definite nice look to it. It turns out this is actually not the most efficient way to do it. Neither is substitution, neither is elimination. There's really a more efficient, quicker, easier way, but we'll leave that for a later course. Down the road, if any of you finally take a course called linear algebra, people usually take it after they've completed calculus. If you were in my linear algebra classes, we would talk about that most efficient way. But this actually it has a certain beauty, it has a certain poetry. Am I going to ask you to do a Cramer's rule for a 3 by 3 system? I reserve the right to. I probably won't. Because if this drives you crazy, who could blame you? Nobody could blame you. but I at least wanted to show you this. Cramer's rule for a 3x3 system. Okay, now, chapter 5. Well, there's some good news. There's some good news. Oh, there's one more section in chapter 4, the final section in chapter 4. I want to put that on hold. So the final, let me make sure I've got the, I don't want to lose. Let's see if I go to this. Am I gonna? Yeah, the final section in the final section is 4.7 in chapter 4. Let's not do that. Let's skip that. That will not be on the next test. We are going to come back to that. Eventually, we're going to do a topic called linear programming. And when we do that, we'll loop back to that. So now it's onwards to chapter 5. And chapter 5 is, you can have a little breather. Things are a little bit easier here in chapter 5. We talk about polynomials, but in the easiest sort of way first, really. Like, for example, what is a polynomial? Well, I mean, you've seen examples of polynomials. Hey, when you were a kid, no one gives you the official biological definition of a cat or of a penguin or of a giraffe. They show you examples. For example, they go, hey, that's a cat, that's a cat, that's a cat. Oh, that's a dog, that's a dog. And then you sort of get the hang of it. You say, oh yeah, I know what a dog is when I see one, and I know what a penguin is when I see one. I know what a tiger is when I see one, and I know what an insect is when I see one. Then down the road, you can say, what is it really that makes or constitutes a cat? What is it that really causes a tiger to be a tiger? Or what, how do you officially classify an object as a tiger? But you do that later. Now, you've seen polynomials. So this is a polynomial, 3x minus 7. And this is a polynomial. And this is a polynomial. And this is a polynomial. So you've seen polynomials for years now. And in a lot of ways, we don't really have to worry about the official definition. I mean, what does it make something a polynomial? For example, that's not a polynomial. And that's not a polynomial. And that's not a polynomial. This is 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 not a polynomial. So none of these are polynomials. None of those are polynomials. But the upper ones here are. So, what really is a polynomial? Well, okay, a little quick aside here. Consider the following. Consider this. X squared plus x plus 1. 1 plus x squared. This is called descending order, because if you look at the exponents of x, they're descending. Here it's descending order. It does not make any difference whatsoever which way you write your polynomials, your choice. I would say the majority of the time we probably tend to write them like this, but these two are absolutely the same thing. I guarantee to you that these two are the same thing. So you can always write it either way you want. Now, when I give the definition of a polynomial, I'm thinking right now, okay, which way would be maybe easier to use in the definition. So a polynomial, P for polynomial, is a function of x. And maybe the easiest way to write it is this. Think of the easiest way to write it right now. Let's say a sub, you may or may not like this, but a sub 0 plus a sub 1 x to the power of 1 plus a sub 2 x squared plus dot 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 plus a sub n times x to the power of n. And what that means is we just start off with a number and a number times x and a number times x squared, and we keep on going up to some point. So n just represents the end of the polynomial. Now n could be 2, n could be a billion, n could be a Google or a Googleplex. So that's what a polynomial is. Now, what we do here in chapter 5 at first is we learn how to add, subtract, divide, and multiply polynomials. And the adding and subtracting, the really good news here is you do exactly what you think you would do. So let's just go ahead and do an example here. Let's say we had 5x cubed plus 4x squared minus 7x plus 9. And let's say we want to add, and I can write the addition going off in that direction. It doesn't matter. Plus, let's say x to the 4th minus 2x cubed plus 3x squared plus 7x plus 1. Here's one polynomial plus another polynomial. And the good news is, what do you think you would do? You think you would just add like terms, and that is exactly what you do. So, you know, I just look at this as a long string of terms. Each one of these terms is called a monomial. Some of this terminology doesn't really matter, but maybe you should know it, I guess. So this term right here, the number times x raised to a power, anytime you have a number, let's just say a number c times x raised to a power, where the power is a positive whole number, that's called a monomial. So this little term up here is called a monomial. I only have one x to the fourth term, so there's that term. I have 5 of these, 5x cubes minus 2x cubes. Well, 5 of these minus 2 of these is 3 of those. So I took care of that. 4x squared plus 3x squared, I've got 4 of these and 3 of these, so that's 7 of those. I've got negative 7x's plus 7x's, so that's 0, that's gone, and 9 plus 1 is 10. So when you do addition and when you do subtraction, you just combine like terms. And so it's probably better if I say no more, because you'll naturally do the right thing. But let's talk about multiplication, which I don't know, it's not as obvious, it's not as natural. But let me start off with a fairly easy example, which I think you're probably all incredibly familiar with. And that is where we do the proverbial FOIL method. Now, if you never heard the term FOIL method before, fine, it doesn't really matter. It stands for first, outer, inner, last. But how do I multiply this polynomial by this polynomial? We take this times this, and this times this, and this times this, and finally this times this. Everything gets multiplied by everything else. I suppose I feel obligated to, I don't really think of it as the FOIL method. It's kind of not how I think about it. I just think about it as this pattern. But you multiply the first 2 terms and the outer 2 terms and the inner 2 terms and the last 2 terms. So that's where this idea of FOIL method came from. You know, I should probably at least once, because I think it's good to see, why on earth is this the way it is? You know, why is that the way it is? Let me show you. Suppose you had star plus W times T plus H. Now, the distributive rule is a rule. You can do the distributive rule because we declare it. It's an axiom. It's a rule of the game. So if I look at this as one object, look at that as one object, take this times this and this times this, you'd have star plus W times T plus star plus W times H. Now I'm allowed to do that, so to speak, because it's the distributive rule. Enough said. Now I can do the distributive rule again. This times this times this. So star T plus WT plus, and then here, H star plus WH. And look, star T right there, star H, well, it's there, WT is there, and WH is there. So the FOIL method, or whatever you want to call it, it is a shortcut for doing the distributive rule twice. Actually, 3 times. Once, twice, 3 times. So is it a shortcut? Yeah. Is it a good shortcut? You bet. Yeah, I never do it this long way. But there, now you've at least seen that, yeah, you can prove that the FOIL method is based on our original axioms or assumptions. Now, as far as the FOIL method goes, is the FOIL method important? Let me write down another example. Let's say we have 5x minus 1 and 3x plus 2. Is being able to do this important? Absolutely. Absolutely. You really need to be able to do the FOIL method with, you should not be looking at your notes. You should not be going online. You should look at that. You should be able to do it in your sleep. You should be able to do it with the greatest of ease. And there's a way to tell if you can. Let's go ahead and do this. So this times this, and this times this, and this times this, and this times this, and let's combine like terms. Here's how you can tell when you got it. Is when you don't need to, not only don't you need to write that down, you won't want to write that down. You'll just do that in your head. Now that's assuming the numbers are fairly tame. I mean, these are single digit whole numbers. Make them really gigantic numbers or fractions, hey, then of course, write it down or whatever, all bets are off. So let me do one more example. I don't know, suppose we add negative 3x plus 5 and 7x plus 1. So I think, okay, this times this, negative 21x squared, negative 3x plus 35x, so plus 32x, and then plus 5. That's about how long it should take you. If it takes you much longer, you need to practice on it more. And you'll see why coming up. It is absolutely important that you can do the FOIL method, and honestly, do it quickly and do it with very little strain. I mean, it should not feel like it's tasking your mental powers. Here's the good news. Even if you never did this before in your life, never in your life, if you did 30 or 40 problems, you'll probably be an expert. I can't say that about many things in mathematics. Very few things can you say, oh, do 20 examples and you'll be an expert. But you do 20 or 30 or 40 or definitely 50 of these, you'll be great. So the first thing I really need you to work on is the adding, subtracting polynomials. That it just never seems to give anybody any trouble, and everybody's great. But if it gives you trouble, remember, ask me, ask questions. We'll have another office hour this Friday, and I'm going to be announcing office hours soon at a different time for those of you that can't make that office hour. But hold on, let me check something here. Yeah, this is from 5.3. 5.1 is pretty easy, but if you have any questions, let me know. 5.2 I want to talk about is a separate, it'll actually be the next video, separate video. So this stuff is 5.3. You want to practice this. So again, this is 5.3, multiplying polynomials. You want to get very good at this. Absolutely have this under control. Next video I'll talk about, or I'll discuss, is 5.2. So this is 5.3, next video, 5.2. Now it's out of order, but 5.2 you can kind of talk about a little bit out of order, and I feel like it needs its own separate video. It's not that it's super difficult, but it really should, I think, be a separate topic. So until I see you next video, goodbye.